Alright, we're going to look at Module 5, Section 1, which is our first section on rational expressions. Now, a rational expression simply is a quotient of two polynomials. Now, polynomials, if you remember, are our powers and variables all put together, and a quotient is a fraction of the two. So, an example of a rational expression would be if I take a polynomial, say 2x plus 1, and I put that on top of x squared minus 4. So that would be a rational expression. Now, the rational expressions are a kind of unique type of relation, as they are the first one that has an interesting domain. Now, domain, if you recall, domain are the possible x values that would work in a relation. It's the x values you can plug in. And so the domain, we say, are all x values that can be plugged in into an expression. Now you might say, well, that's everything, but some relations you can't plug certain x values in. They don't work. And a rational expression is a really unique one of those cases. Let's just look at, before I give you the definition of a domain of a rational expression, let's just look at an easy one. X over x minus 1. Now, if you think about it, what x can you not put into here? Well, I know I cannot put 1 in here, because if I plug 1 in for x, I'll have 1 over 1 minus 1, which is 1 over 0. You can never have a 0 on the bottom, or this is what we call undefined. So this is actually not allowed. So the domain of every rational expression, we say, is all real numbers, except those that make the bottom 0. So in the problem we just saw here, this example, so we know that 1 is a problem, because 1 minus 1 will give us a 0 on the bottom. So we write our domain like this. We say the domain, we say, is all real numbers, and you can use the R with the bar through it. This represents all real numbers, x not equal to 1. So for this problem, we would basically exclude 1. We can plug any number in and it'd be fine except for 1, because when you plug 1 in, you get a 0 on the bottom, which is a problem. Okay, so let's look at some examples here. We want to determine if the following are rational expressions. Now we said rational expressions are simply going to be quotients of two polynomials. So really all we have to look for are these polynomials. Well, this is a polynomial and this is a polynomial because it's just powers and sums and signs of different numbers and variables. So these are both polynomials. So we say yes, it is rational. Okay. Now for B, we see one of these is not rational because this is a polynomial, x squared minus 9, no problem, but this is a square root. So we say this is not rational because the square root of x minus 3 is not a polynomial. So one that is, because it's just two polynomials, one that's not. One thing I like to think about for whether something's a polynomial, you can think of, is it something that you can factor, is in one of those kind of nice forms we've seen. If it is, it's typically a polynomial. If not, it's not. Okay, the second kind of problem is dealing with that domain problem. We can think about, okay, determine what values are excluded from the domain in each rational expression. So basically, what can x not equal? Now in these problems, it's kind of a hard thing, but what we really have to do is we ignore the numerator altogether. So we just look at x minus 1, or x plus 1, pardon me, which is the bottom. So when I look at x plus 1, I want to know what values for x plus 1 will make the bottom 0. What would I plug in for x to make it 0? What number plus 1 equals 0? Well, if you set this up, you could simply just subtract 1 from both sides. So negative 1 would make the bottom 0, so we exclude that value. I cannot plug negative 1 into this function, or this relation, or it'll give me an undefined value. It'll give me something over 0. Okay, so same thing in the second one, but you see the denominator is a little more complicated. It's x squared minus 5x plus 6 equals 0. Now this is a quadratic relation, so we want to figure out what would make this 0, and then we'll exclude those values. Now you can do this a million different ways, but the easiest way I think is to factor. And it's always a good practice to factor. So we'll factor, since there's 3 terms, using our rectangle method. So I'll take 1 times 6, which is 6. I need 2 things that multiply to 6 but add to negative 5. That would be negative 3 and negative 2. So when I set my box up, I have x squared, I have 6, I have negative 3x, and I have negative 2x. So I'll pull out an x and a negative 2 from the first 2 rows, and I'll pull out an x and a negative 3 from the 2 columns. So my 2 factors would be x minus 2, x minus 3 equals 0. And you'll notice that these 2 numbers we found are the same 2 numbers that are in our factors. And that is always true as long as this number out front is 1, which in this case it is. So we can kind of save ourselves some time factoring when we do it with 1, because we're going to be doing a lot of that. So we take these 2 factors, set them equal to 0, just like we did. Add 2 to this one, add 3 to this one. So x is 2, x is 3. So in our problem, x can't be 2 or x can't be 3. Those are problems because they would make the denominator 0. Now the second thing we're going to look at in this section is simplifying rational expressions. Now if I go back to basic math and think about a fraction, say 2/4. 2/4 is a good fraction, but we already know this reduces to 1/2. So we're going to do the same thing with these rational expressions by what we say canceling out common factors. But the key thing is here, we're going to factor and then we're going to cancel. So to simplify these more complicated fractions, rational expressions, we're going to factor the top and bottom and cancel anything that's the same. If you start trying to cancel things out, it's not going to work. You have to factor first. Okay, so let's look at our first problem, which is 4x minus 8 over 10x minus 20. So the first thing I always look for when I factor is a common factor. And I can see that these top ones both divide by 4. So I will factor a 4 out of the top 2. I can divide them both by 4, so I take a 4 out. If I look at the bottom ones, I can take a 10 out because it's 10 and 20. They both divide by 10. And so I take a 10 out of 10x, I have x, a 10 out of 20, and I have 2 left. So now we've factored. So a very key thing, you have to factor first. Now, if you see something that's the same, like the x minus 2's, you can cancel them out. So those now are gone. And now if you think of 4/10 as a fraction, how does 4/10 reduce? Well, it's 2/5 because they both divide by 2. So if you think about it, this rational expression I started with actually can be simplified to just simply 2/5. So by factoring and canceling out anything that's the same, you get a much simpler expression. But again, like most things we'll do in this chapter, a lot of factoring. Okay, let's look at this one. So the bottom is x minus 9. I don't really see too much that's going to factor out of there, so it's just going to basically stay as x minus 9. Now the top, I see a 2x squared and an 18. Those are both even, so I can start by taking a 2 out. I'll take a 2 out front as a greatest. And that'll leave me x squared minus 9. So now if I think about x squared minus 9, if you remember, that's a difference of squares, because that's x and x, and this is 3 and 3. So this factors as 2, x minus 3, x plus 3, all over x minus 9. So I took a 2 out of the top in the first step, and then I recognized difference of squares. Remember, if two things are perfect squares, x and x, 3 and 3, you can factor it as x minus 3, x plus 3. Now, if you look at this, nothing cancels, right? I see an x minus 9 here. These on top, nothing cancels, so it can't be reduced. So that is the simplest term of this rational expression. It's very similar to a fraction like 2/3. 2/3 doesn't simplify. It just is what it is. Okay, let's look at C. Alright, so now these are a little more complicated factors. So I'm going to kind of put these out to the side. Well, first I'll look if I can divide any of them by anything. The bottom one has a 1, so I really can't change that. But if I look at the top one, I have a 4, a 16, and an 84. So I actually can divide all of those by 4. So I could take a 4 out. I'll be left with x squared minus 4x minus 21. And then I'll have x squared minus 5x minus 14 on the bottom. So now these guys, the x squared minus 4x minus 21 and the x squared minus 5x minus 14, those very well may factor further. So I'm going to write those down here, and I'm going to think about factoring them a little further. Now the good news is they both have a 1 in front. There's a 1x squared and a 1x squared. So when I think about 1 times negative 21, that's negative 21. All I have to really think about are what are two numbers that multiply to negative 21 and add to negative 4. And this is really the trick of factoring. Well, I know this is negative 7 and positive 3. Negative 7 times 3 is negative 21. Negative 7 plus 3 is negative 4. And this is the thing that you really need to work on. So this one factors as x minus 7 and x plus 3. Now we'll put it back in the context of the regular problem here in a second. So, but this guy on top now is 4 x minus 7 x plus 3. And that's just this whole top here that I've now factored. And now I'll look at the second one that we're looking at. And we know it's negative 14. So I'm thinking, are there two things that multiply to negative 14, add to negative 5? Remember, if it's 1 in front, it multiplies to this, adds to this. And that would be negative 7 and positive 2. So it would factor as x minus 7, x plus 2. So that's the bottom here. So I'll put that here. So once you have it factored, the rest is relatively simple. It's the factoring and getting this original to look like what it does down here. I can cancel the x minus 7s, and that is all. So this will be 4 x plus 3 over x plus 2. Okay, let's look at D. Now, if you look at D, the top is 2x squared minus 5x plus 3, nothing I can take out. The bottom is 4x squared minus 9, nothing I can take out. So let's kind of look at these two polynomials, try to factor these individually. Now this does have 3 terms, but it's not 1 in front. Remember we had talked about if there's 1 in front, it's a relatively simple process. This doesn't, so I'm going to go back to our rectangle method. So 2 times 3 is 6. First times last is 6. So I'm thinking two numbers that multiply to 6 but add to negative 5. Well, that would be negative 3 and negative 2. And if you like doing this rectangle for all the problems, you can, but it just takes a little time. So when it's 1, I don't do the rectangle. But if it is a number that's not 1 in front, I'm definitely going to do it. So we have the negative 3x and the negative 2x in these two boxes. So I'll take an x out of the first two. Now the bottom I have negative 2x and 3, which I can't take anything out. But remember, since if the first term's ever negative, you want to take that negative out. So I'll take negative 1 out. For the first column, I can take out 2x. And for the second column, I can take out 3, but since the first one's negative, this guy's negative, I'll take out negative 3. So this is going to factor as x minus 1, which is the stuff on the left, and 2x minus 3, which is the stuff on top. So our problem here is going to be 2x minus 3 and x minus 1. But that's just the top. That is the trick to these problems. There's quite a bit of factoring to each problem. So now on the bottom here I have 4x squared minus 9. There's only two terms. Whenever there's two terms, it's typically going to be difference of squares. 2x and 2x, 3 and 3. So difference of squares, if they're both squares, it's just the first one minus the second one, the first one plus the second one. So I can write those up top. 2x minus 3, 2x plus 3. And if you look at this, the 2x minus 3's are the same, so they will cancel out. So our answer is going to be x minus 1 over 2x plus 3. Okay, let's look at one more problem. Now the last problem, 3x squared y7, 27xy 12. Good and bad news here. There is no factoring because there's no pluses, there's no minuses, nothing like that. So really, we'll just look at each one individually as a fraction. So 3 over 27, I can simplify that because they both divide by 3. So 3 divided by 3 is 1. 27 divided by 3 is 9. So this is like normal stuff. 3/27 is 1/9 reduced. Now if I look at the x's, I have x squared on top and x1 on the bottom. So if you think about it, that's x and x on the top and 1x on the bottom. So I'll cancel out basically one pair of x's and I'll have an x on top. And now for the y's, I've got y12 on the bottom and y7 on top. Now the same principle applies. We'll subtract those exponents. So 12 minus 7 is 5. But I'm going to put those on the bottom. I'm going to put those on the bottom because there was more on the bottom. So if you think about what this would actually look like, there basically would be 7 y's on top. Because y to the 7 means y, 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 y. And there'll be 12 y's on the bottom. So basically all these y pairs would cancel out on top, and there would just be these 5 y's left on bottom, which is why I put them on bottom. Now this problem had no factoring, but it's just kind of odd, because you have some problems where you need factoring, but there's these couple that you don't. So basically the rule, if there's no plus signs, no minus signs, it's just basically monomials, you can just do these kind of exponent rules that we've always known. Alright, well that's all for section 5.1. Please let me know if you have any questions as you proceed with the assignment.